I'm going to try to make this quick. The content for this week is about magnetic field produced by currents. And that's something that we talked a little bit about a couple weeks back. But the only thing we really did with it was like our right-hand rule thing, where you let your thumb be the direction of the current, and then your fingers told you which way the field went. I can show that here. These are the two different right-hand rules that we've talked about. And again, this upper one is the only thing we've really said so far about the magnetic fields that currents make. And then we also had this lower right-hand rule. Anything that involves a force, you have to use this lower rule. But if you just want to know about the field that's produced by a current, you can use the upper rule. So the strength of that magnetic field gets weaker as you move away from the wire, which is probably not too much of a surprise to you. The formula that describes it is here. Remember, B is the symbol for magnetic field, I is the amount of current, R is the distance to the wire where you want to measure the field. And so as R goes up, B goes down, which means that the field gets weaker when you move away. One thing to keep in mind is that this formula only works for very long, straight wires. The wire has been like bent into a circle or something like that, this formula doesn't work. If the wire is like relatively short, it doesn't work, but it has to be quote unquote long, which to a physicist means infinite, basically, in order for this formula to work out so simply. Now you can find the magnetic field for any arbitrary wire, curved or not, short or long, but it's very complicated. So this is like a special case formula. This other symbol in here, the mu sub 0 or mu naught, that is called the permeability of free space, and that is the fundamental magnetic constant for the universe. When we were studying electricity, you might have seen an epsilon naught at some points, and that's the electric equivalent of this magnetic constant. So it's just a number that you need to get things to scale correctly. So we already are aware that if a current is flowing through a magnetic field, there will be a force exerted on the wire. And so as you can imagine, if there are two wires, each one of those wires creates a magnetic field, and that means that the other wire is carrying a current through that magnetic field, which means that there should be forces involved if you just have two wires. So what I've done here is I took the force on a wire formula that we messed with a few weeks back, F equals ILB sine theta. And all I've done is replace the B with that magnetic field formula from the other slide. There's some subscript in here to keep track of like which wire is which. But it results in this. So the force, the magnitude of the force exerted between two wires depends on each of their currents, depends on how long they are, and it depends on how far apart they are. This formula is kind of qualitatively similar to something like Coulomb's law for electrical forces. That would have had like Q1 times Q2 in the numerator, and this has I1 times I2 instead. The primary difference between this and those force laws that we saw before is that the distance in the denominator is just an r instead of an r squared. That's related to the fact that the magnetic field is being produced by a line instead of by a particle. And so that changes the geometry of the problem. That's why it's an r instead of an r squared. So figuring out whether they attract or repel is something that in practice you could just memorize, but I want to talk about how to reason through that. So I've got two parallel currents here. Both of them are going to the right, I1 and I2. And what I want to do is figure out the direction of the force felt by wire 1, the blue wire. So I know that wire 2, the red one, is going to make a magnetic field as I've drawn it here. Below the wire, the field goes into the screen. Above the wire, the field comes out of the screen. On the right, I've redrawn it from another angle. So here the currents are coming out of the screen. And if current 2 is coming out of the screen, I know that the magnetic field produced by it makes this counterclockwise circle. And all of that you can figure out with the first right-hand rule, the production rule, where you let your thumb be the current. So current 1 is flowing to the right through a magnetic field that comes out of the screen. And if I use the forces right-hand rule, it's probably not going to look right when I do this in the camera, but it's supposed to be I, L, B. So the first vector is the current I, which goes to the right. I can see it looks like it's pointing left, so you'll want to do this on your own screen. But I'm pointing my entire hand in the direction of the current, and then I need to bend my fingers so that they're in the direction of the field. The field is coming right at me, so that's really hard to do. But the result is that I have my thumb going down, which means that the force on the blue wire points down. If you go through that whole process for the other wire, like if you figure out which direction does the blue magnetic field point, what force does that exert on the red wire, you'll find that it's going to be the opposite. And that shouldn't be too surprising if you think back to Newton's laws. If the force of wire 2 on wire 1 goes down, then force of wire 1 on wire 2 needs to go up. They have to be opposites. So if the two currents go in the same direction, the wires are going to attract each other. And conversely, if the currents go in opposite directions, so if the currents are anti-parallel, that will make the wires repel from each other. So in this new diagram, the only thing I did was reverse the x's and the dots because the current was going left, and that results in the force also getting reversed. So again, that's something that you can just memorize if you want. Parallel currents attract, anti-parallel currents repel. But it may feel a little backwards, because if you think about either magnetic poles or electric charges, usually we say that opposites attract and like things repel from each other. But this kind of feels like backwards from that. What's really going on is that you need to think about the two magnetic fields in the area where the in between the wires. So I have this diagram in the bottom. In this case, where both of the currents come out of the screen, if you look at the magnetic field in the middle region, those fields are opposites. And that is why those wires attract each other. Whereas if the currents have opposite directions, then in this space between the wires, the two fields go in the same direction, and that's why they repel. So if you want to stick with opposites attract, you need to think about the field direction instead of the current direction. And that is all I have got for this week. I encourage you to look at this stuff in the book also. And I posted a fun old black and white video, which I think is a nice demonstration of these forces. And then see how the work goes. Hope everyone is healthy and happy.